Welcome to Sleepy Construction. Close your eyes and let's build. Tonight, we are going back. Not as far as last time, only 140 years or so. Back to a city of gaslight and cobblestone. A city preparing to show the entire world something it had never seen before. Paris, in the late 1880s. A city about to host a World's Fair. And a city about to argue, loudly, publicly, and for years, about a single iron tower that a bridge engineer wanted to build at its very center. Tonight, we build the Eiffel Tower, slowly, girder by girder, rivet by rivet, just the way they did. If you'd like to keep building with us, night after night, a like and subscribe helps this small channel grow. And if there's a structure you've always wondered about, tell me in the comments. We may just build it together next. You don't need to remember any of this. You don't need to follow every detail. You can simply let the story carry you, the way the iron once rose over the rooftops of Paris. So settle in, get comfortable, and let's begin. In 1884, the French government began planning something enormous, though not in the way we usually mean that word. They were planning an event, the 1889 Exposition Universelle, a World's Fair timed deliberately to mark the 100th anniversary of the French Revolution, intended to showcase France's industrial, scientific, and artistic achievements to visitors arriving from every corner of the globe. World's fairs in this era were enormous undertakings and enormously competitive ones. Each host nation wanted its fair to be remembered as the grandest, the most impressive, the most talked about in the world. And every great fair, organizers understood, needed a centerpiece, something so tall, so striking, so entirely new, that it would become instantly recognizable, a symbol really more than a building. A competition was announced, open to any engineer or architect in France, inviting proposals for a structure that could serve as the fair's dramatic entrance archway, positioned at the base of the Champ de Mars, a long public park stretching out before the military school. The requirements were, on paper, simple. It needed to be tall, taller, ideally, than anything ever built before. Over 100 submissions arrived. Proposals for towers, monuments, and strange imaginative structures of every kind. One, quite memorably, suggested a gigantic guillotine-shaped monument, an idea that, understandably, went nowhere, given its rather unfortunate association with a period of French history. The organizers were eager to commemorate more gracefully. Other proposals included an enormous water sprinkler intended to cool the entire city during hot summer months, a gigantic lighthouse designed to illuminate all of Paris at night, and several variations on a purely decorative tower with little serious engineering justifications behind their impressive height claims. Many of these rival entries suffered from the same basic flaw: grand, ambitious sketches lacking the detailed structural calculations necessary to convince the selection committee that they could actually be built safely, on budget, within the demanding timeline required before the fair's opening. But one submission stood apart from the rest, not because it was flamboyant or symbolic, but because it was rigorously, mathematically, structurally sound. It came from the engineering firm of Gustave Eiffel. Gustave Eiffel was not, at this point in his career, an unknown figure. He had already built a considerable reputation as one of France's most accomplished structural engineers, specializing particularly in iron construction, bridges, viaducts, and large metal frameworks designed to withstand enormous stress across long spans. Among his most notable earlier achievements was the Garabit Viaduct, a railway bridge in southern France that, at the time of its completion, was the tallest bridge in the world. A striking arched iron structure that demonstrated Eiffel's deep, practical understanding of how metal behaves under load, particularly wind load, a factor that would prove absolutely central to the tower story we're building tonight. Eiffel had also, notably, contributed the internal iron framework supporting the Statue of Liberty, working alongside the statue's sculptor to design a skeleton strong enough to let the copper skin move slightly with temperature changes and wind, rather than cracking under rigid stress. This experience with the Statue of Liberty proved particularly relevant to the tower project, since both structures required Eiffel to think carefully about how a large, exposed structure would need to flex and respond to environmental stress over time, rather than simply resisting such stress through sheer rigidity and mass. Beyond these two famous projects, Eiffel's firm had also completed dozens of railway bridges throughout France and abroad, including several significant projects in Portugal, Hungary, and various French colonial territories, establishing a reputation for reliable, on-time delivery of technically demanding iron structures. A reputation that would prove essential when it came time to convince skeptical government officials that his firm could realistically complete the tallest structure ever built within a mere 2-year window. Eiffel was, by the mid-1880s, a wealthy and well-respected figure within French engineering circles, known for a particular combination of mathematical rigor and practical business sense that distinguished him from purely theoretical academics on one hand and purely commercial contractors on the other. This combination would prove essential throughout the tower's construction, since the project demanded not only sound engineering calculations, but also careful financial planning, skilled project management, and the ability to coordinate hundreds of workers and 18,000 individual iron components across a demanding 2-year timeline. So when the competition for the 1889 World's Fair centerpiece was announced, Eiffel's firm didn't submit a symbolic sketch or an artistic vision. They submitted an engineering proposal, the actual design, the specific curved tapering profile that would eventually rise 300 meters above Paris, is generally credited to 2 engineers working within Eiffel's firm, Maurice Koechlin and Émile Nouguier, with architect Stephen Sauvestre, later refining the design's aesthetic details, adding decorative arches at the base and other embellishments to soften what might otherwise have looked like a purely industrial structure. Eiffel initially showed only modest interest in the concept when his engineers first presented it. It was only after Sauvestre's aesthetic refinements that Eiffel became genuinely enthusiastic, purchasing the patent rights to the design himself and championing it aggressively through the competition process. His proposal wasn't merely the tallest. It was, critically, the most convincingly buildable, supported by detailed calculations, addressing exactly the kind of skepticism such an ambitious structure was bound to attract. In June of 1884, the design was formally patented. In May of 1886, following considerable negotiation over financing, Eiffel's proposal was formally selected. Construction was set to begin the following year. with an extraordinarily tight deadline. The tower needed to be structurally complete in time for the fair's opening in May of 1889, just over 2 years, for a structure taller than anything human hands had ever built. Before a single foundation stone was laid, Eiffel and his engineers faced a challenge more fundamental than height alone. Wind. Any structure this tall, rising far above the surrounding rooftops of Paris, would face wind forces unlike anything most buildings of the era needed to consider. A rigid, solid tower of this height, if built without accounting properly for wind resistance, risked catastrophic failure, swaying, cracking, or in the worst case, toppling entirely. Eiffel's background in bridge engineering, where wind load calculations were already a matter of routine, careful practice, proved essential here. The distinctive, gently curving shape of the tower, narrower at the top, flaring outward toward the base, wasn't primarily an aesthetic choice. Though it does read as elegant even today, it was a mathematical one. Eiffel calculated the tower's curve using a method that essentially traced the exact profile a structure would need in order to offer equal resistance to wind at every point along its height, a shape sometimes described informally as the curve of least resistance. Picture the wind pressing against the tower as a slow, steady force, rather than a single dramatic gust. At the base, the structure needed to be wide to resist bending under horizontal wind pressure. As height increased, less material was needed at each successive level, since less lateral force needed to be resisted the higher one went, relative to the mass supporting it below. The result of these careful calculations wasn't a rigid, blocky monument, but rather an open, latticed structure, thousands of individual iron pieces, riveted together into a framework strong enough to bear its own weight and resist significant wind, while remaining, remarkably, mostly empty space. In fact, if you were to somehow melt down every piece of iron in the Eiffel Tower and pour it evenly across the base of the structure, the resulting layer of iron would be only a few centimeters thick. The tower is, in a very real sense, mostly air, held together by a precisely calculated lattice of iron. This lattice design carried another crucial advantage. It dramatically reduced wind resistance compared to a solid structure of equivalent height, since wind could pass directly through the open ironwork rather than pressing against a large, solid surface. Even today, during the strongest storms, the tower's very top sways only a small amount, typically no more than around 12 centimeters, a testament to how thoroughly Eiffel's original calculations accounted for exactly this kind of stress. More than a century before modern wind engineering software existed to double-check his work. It's worth pausing on just how remarkable this calculation method truly was for its time. Eiffel and his engineers didn't have access to wind tunnels, computer modeling, or any of the sophisticated testing equipment modern engineers rely on when designing tall structures today. What they had instead was careful mathematical theory, painstaking manual calculation, and Eiffel's own considerable practical experience gained from decades of building bridges that needed to withstand real-world wind conditions across wide, exposed river valleys. Maurice Coquelin, the engineer most directly responsible for the tower's underlying mathematics, spent considerable time refining equations that modeled wind pressure as a function of height, surface area, and the tower's specific tapering profile at each level. These calculations needed to account for a subtle but critical detail. Wind pressure doesn't simply increase steadily with height in a straightforward, linear way. Rather, it behaves in more complex patterns, influenced by the specific shape and openness of the structure it encounters. The lattice design, by allowing wind to pass through rather than press directly against a solid surface, dramatically reduced the effective pressure the calculations needed to account for, compared to what a solid tower of equivalent height would face. This is, in many ways, the same underlying principle sailors have long understood about sails and rigging, and the same principle modern engineers now apply routinely when designing skyscrapers, suspension bridges, and other tall or long-span structures exposed to significant wind loads. Eiffel, characteristically, wasn't satisfied with theory alone. Throughout the tower's design process, and indeed for years after its completion, he continued conducting his own practical wind resistance experiments, a pursuit we'll return to later in tonight's story. Once the tower was finally complete and available as its own full-scale laboratory, with the mathematics settled, construction could finally begin. In January of 1887, the tower's design called for 4 enormous supporting legs, arranged in a wide square base, each leg angled inward as it rose, gradually converging toward a single point far above. Each of these 4 legs required its own deep, carefully engineered foundation, capable of supporting an enormous concentrated load. 3 of the 4 foundations, positioned on relatively stable, dry ground, were completed using fairly conventional methods for the era. Deep excavation, followed by thick layers of concrete and masonry, designed to distribute the tower's weight evenly into the earth below. The 4th foundation, however, sat close to the Seine River, where the ground was considerably softer and wetter, closer to the water table. For this foundation, Eiffel's team employed a specialized technique using compressed air caissons, essentially large, airtight chambers sunk into the riverside ground, with compressed air pumped inside to keep groundwater from flooding the excavation, while workers dug down to a stable foundation layer. Workers operating inside these pressurized caissons faced genuinely difficult, specialized conditions, working in compressed air at meaningful depth below the surface. Conditions that, in this era, were not yet fully understood in terms of their physiological risks. Though Eiffel's project, fortunately, avoided the serious decompression injuries that plagued some other major projects of the period using similar techniques. It's worth slowing down a little on this particular technique, since it represents one of the more genuinely dangerous, if quietly unremarkable, aspects of the tower's construction. A caisson, in this context, was essentially an enormous upside-down box, open at the bottom, sunk into the soft riverside ground and sealed at the top, with compressed air pumped continuously into the interior space to push back against the groundwater trying to flood in from below. Workers entered and exited this pressurized chamber through an airlock, gradually adjusting to the increased air pressure inside, then spending hours at a time excavating soil and rock from the chamber's floor, gradually deepening the foundation pit as the entire caisson structure slowly sank further into the ground under its own weight, and the weight of masonry being added above it. This work required workers to breathe compressed air for extended periods, a practice not yet well understood in terms of its effects on the human body. The same underlying phenomenon that would later be identified and named decompression sickness, or, more informally, The bends, once too rapid decompression after working in similar pressurized conditions, began causing serious, sometimes fatal injuries on other major engineering projects of this general era, particularly certain bridge and tunnel projects in the United States happening around the same period. Eiffel's own project, fortunately, proceeded without similarly severe incidents, likely due to the relatively modest depth required for this particular foundation compared to some of the more extreme caisson work being attempted elsewhere in this period, combined with reasonably careful, if not yet fully scientifically informed, working practices adopted by the supervising engineers. Once the caisson had descended to a sufficiently stable layer of ground, the chamber was filled permanently with concrete, creating a solid, reliable foundation capable of supporting its share of the tower's considerable weight, indistinguishable, once complete, from the three more conventionally excavated foundations supporting the tower's other legs. Each of the four foundations needed to be positioned with extraordinary precision, since the entire tower's four legs needed to converge accurately at a single point far above. Despite starting from four separate, independently constructed foundations spread across a wide base, surveying and measurement, much like our story from the pyramid last time, played an enormous role here. Careful, repeated calculation, ensuring that each foundation was positioned exactly where the overall design required, so that months later, when ironwork began rising from each leg independently, the entire structure would still meet correctly at its center. By June of 1887, the foundations were complete, and the true work of the tower, assembling its iron skeleton piece by piece, could finally begin. One of the quiet, remarkable secrets behind the tower's astonishingly fast construction timeline lay not at the construction site itself, but at a factory workshop in the Parisian suburb of Levallois-Perret. Rather than shaping and fitting iron pieces on site, as was common practice for large ironwork projects of the era, Eiffel's team designed the entire tower using a system of careful, advanced prefabrication. Every single piece of iron, and there were approximately 18,000 distinct pieces in total, was individually designed, drafted, and manufactured at the workshop, then labeled with a precise reference number indicating exactly where it belonged within the tower's overall structure. This was, in effect, one of the earliest and most ambitious applications of what we might now recognize as modular, standardized manufacturing, applied to a structure of genuinely enormous scale. Engineers produced more than 5,000 detailed technical drawings to specify every single component, its exact dimensions, its precise angles, the exact position and number of rivet holes required to connect it to its neighboring pieces. This meant that when a piece of iron arrived at the construction site in central Paris, workers didn't need to cut, drill, or significantly modify it on site. They simply needed to lift it into its predetermined position and begin the riveting process, a workflow that dramatically increased both the speed and the precision of assembly compared to methods requiring extensive on-site fabrication. Consider for a moment the scale of coordination this required. 18,000 individual pieces, each one unique, each one needing to arrive at the construction site in the correct sequence, at the correct time, to be lifted into the correct position by workers who needed to trust that the piece they were installing would fit precisely. On the first attempt, with pieces installed weeks or months earlier. There was very little room for error in a system like this. A single miscalculated piece, discovered only once lifted hundreds of feet into the air, could delay the entire project significantly. And yet, this system worked with remarkable consistency throughout the tower's construction. A testament to the careful, patient drafting work completed before construction ever began, much like the careful nighttime surveying that preceded the very first stone of the pyramid in our previous story. Let's slow down for a while and picture the workshop itself, tucked away in the Parisian suburb of Levallois-Perret. Considerably less famous than the tower it quietly helped create. Inside, a large industrial building filled with the steady clang and hiss of metalworking machinery. Dozens of draftsmen work at long tables, each bent over detailed technical drawings, translating the tower's overall design into individual, precisely specified components. Nearby, in a separate section of the workshop, metalworkers operate large mechanical presses and shaping tools, bending and cutting iron plates and beams according to the exact specifications provided by the drafting team. Each piece checked carefully against its corresponding drawing before being set aside, labeled and prepared for transport. A young draftsman, we might imagine him named Pierre, though again, his name is lost to history. The way so many ordinary names are, spends his days calculating precise rivet hole placements for a single category of connecting brackets, the kind used repeatedly throughout the tower's lower lattice sections. His work is exacting, repetitive, and largely unglamorous. He will likely never personally witness his specific pieces being installed at the actual construction site miles away in central Paris. He may never fully appreciate, from his workshop desk, just how enormous and celebrated the finished structure will eventually become. And yet, his careful, patient calculations, repeated for bracket after bracket, day after day, form an absolutely essential part of the tower's eventual success. Every prefabricated piece produced at this workshop needed to travel, carefully packed and labeled, from Levallois-Perret to the construction site at the Champ de Mars, using horse-drawn carts and the growing rail network connecting Parisian suburbs to the city centre. This transportation logistics challenge, though far smaller in scale than the river and desert transport we explored in the pyramid story, still required careful scheduling and coordination, ensuring that each piece arrived at the construction site precisely when needed, in the correct sequence, without overwhelming the limited storage space available at the increasingly crowded base of the rising tower. Some historians estimate that at the height of construction, dozens of horse-drawn wagons made this journey daily, each one carrying carefully labeled iron components destined for a specific, predetermined position somewhere within the tower's growing framework. It's a quieter, less dramatic image than Etienne's rivet hammering high above the city streets, or the artist's passionate newspaper protests. But it's every bit as essential to the story. Behind every dramatic rivet driven at height, there existed a small army of draftsmen, machinists, and wagon drivers, working patiently and largely anonymously, translating an ambitious mathematical vision into thousands of individually correct, physically real pieces of iron. Let's slow down for a while and imagine a single ordinary day, partway through construction, sometime in the autumn of 1888. A young riveter, we'll call him Etienne, though we don't know his real name, only that men very much like him made up the backbone of this project, arrives at the construction site before dawn, joining dozens of other workers gathering at the base of the rapidly rising tower. By this point in construction, the tower has already climbed well past the height of most Parisian rooftops, and Etienne's work today will take place high above the ground, on a narrow section of ironwork still being assembled. His team today consists of 4 workers, each with a specific role in the riveting process, a method requiring careful coordination, since each individual rivet needs to be heated, positioned, and hammered into place while still glowing hot before it cools and hardens. One worker tends a small portable forge, heating rivets until they glow orange, then tossing them carefully, skillfully, through open air to a catcher positioned at the exact spot where the rivet is needed. The catcher receives the hot rivet in a metal cone or bucket, then quickly positions it into a pre-drilled hole in the iron framework. A third worker holds a heavy tool called a dolly against one end of the rivet, bracing it firmly in place. And Etienne, today, is the hammerer, striking the opposite end of the still glowing rivet with heavy, rhythmic blows, flattening it into a solid, permanent head that, as it cools and contracts, pulls the 2 connected iron pieces together with tremendous, lasting force. This process repeats, rivet after rivet, all day, hundreds of times, each one requiring precise timing and genuine physical skill. The rivets themselves needed to be inserted while still glowing hot, somewhere around 1,000 degrees Celsius, specifically so that as they cooled, they would contract slightly, drawing the connected iron plates tightly together, creating a bond considerably stronger than a simple cold bolt or pin could achieve. Working at height brought its own particular demands. Workers moved across narrow platforms and temporary scaffolding, often with only modest safety equipment by modern standards, though Eiffel's project maintained a genuinely strong safety record for its era, a source of considerable pride for Eiffel himself, who took safety seriously enough to provide safety belts, screens, and guardrails at a time when such precautions were far from standard practice on major construction projects. Remarkably, only 1 worker died during the tower's entire construction, and that fatality occurred not during official working hours, but when a worker, showing off for a visitor after hours, fell from a platform. Given the scale, height, and duration of the project, this safety record remains, even today, considered genuinely exceptional. By the time the autumn sun sets, Etienne's arms ache from the steady, repeated hammering, his ears still ringing faintly from the day's rhythmic clanging. He climbs down slowly, joining his teammates for the walk home through Parisian streets that, from ground level, still can't quite reveal just how tall the structure rising behind them has already become. Tomorrow, there will be more rivets, nearly 2.5 million of them in total by the time the tower is finished. Rest for a moment in the thought of that number. 2.5 million individual, precise, hand-driven connections, each one holding patiently for well over a century since. While construction steadily progressed, not everyone in Paris was pleased with what was rising above the Champ de Mars. As the tower's iron legs climbed higher through 1887, a wave of public criticism grew alongside it. In February of 1887, a group of prominent writers, painters, sculptors, and architects published an open letter of protest in the newspaper Le Temps, formally objecting to the tower's construction. This letter, often referred to afterward as the Protest of the Artists, or sometimes the Appeal of the Committee of 300. One member, pointedly, for every meter of the tower's height, was signed by a remarkable list of notable cultural figures of the era, including the writer Guy de Maupassant, the composer Charles Gounod, and the architect Charles Garnier, who had designed the Paris Opera House. Their objections were passionate and occasionally quite dramatic in tone. They described the tower using words like useless and monstrous, and expressed genuine fear that its industrial, iron appearance would permanently disfigure the elegant, historic skyline of Paris, a skyline dominated at the time by stone cathedrals, palaces, and classical architecture, rather than exposed iron latticework. Maupassant, according to popular legend, later claimed to eat lunch inside the tower's restaurants, specifically because it was the only place in Paris from which he couldn't actually see the tower itself. Though the full accuracy of this particular anecdote has been debated by historians over the years, the full list of signatories reads, "Today, like a genuine who's who of the Parisian cultural establishment of the era, alongside Maupassant, Gounod, and Garnier, the letter was also signed by the poet Sully Prudhomme, who would later become the first winner of the Nobel Prize in Literature, and the painter William Adolphe Bouguereau, among many other respected figures whose combined cultural authority made the protest genuinely difficult for the government and Eiffel's team to simply dismiss outright. Eiffel, for his part, responded to these criticisms with characteristic engineering confidence, publishing his own defense in the same newspaper, arguing that the tower's grandeur derived precisely from its mathematical purity, that its form followed directly and honestly from the physical forces it needed to resist, and that this functional honesty was itself a legitimate, modern form of beauty, worthy of standing alongside the more traditional architecture the critics preferred. He also, notably, pointed out a practical detail that proved persuasive over time. Unlike the stone monuments the protesters so admired, the tower had been explicitly designed as a temporary structure, with a permit initially granted for only 20 years, after which it was expected to be dismantled. This detail, that the tower's controversial presence was meant to be relatively brief, likely eased some of the immediate public anxiety, even among those who still found its appearance jarring against the historic backdrop of Paris. Public opinion, as it turned out, would shift dramatically once the tower was finally completed and open to visitors. Though that shift, as we'll discuss later in tonight's story, took genuine time, patience, and the tower's own quiet persistence to fully unfold. Through 1888, the tower's four legs continued their steady climb, gradually converging toward the point high above, where the design called for them to unite into a single central structure. This convergence stage presented one of the project's most delicate engineering challenges. Each leg had been rising independently since the completion of its own separate foundation, guided by careful surveying and precise prefabricated components. But the four legs still needed to meet with genuine accuracy at a specific point in space, far above the ground, where no direct physical measurement between them had yet been possible. To manage this challenge, Eiffel's team incorporated hydraulic jacks into the design of each leg's base, allowing for small, precise adjustments to be made even after significant portions of ironwork had already been assembled. a clever engineering safeguard, allowing the structure to be gently nudged into perfect alignment as the legs approached their meeting point, rather than requiring everything to be perfectly correct from the very first calculation alone. By March of 1888, the four legs successfully joined together at the first platform level, roughly 57 meters above the ground, confirming to considerable relief that the painstaking prefabrication and surveying work had succeeded in bringing four independently constructed foundations into precise, unified alignment. From this first platform, construction continued upward, narrowing steadily toward the second platform at approximately 115 meters, and eventually toward the tower's upper sections, where the structure's lattice grew progressively finer and lighter, matching the reduced wind load requirements at greater height. As the tower climbed higher, the logistics of lifting materials became increasingly demanding. Steam-powered cranes, themselves mounted directly onto the tower's own rising structure, hoisted iron pieces upward in stages, with the cranes periodically dismantled and reassembled at higher positions as construction progressed. A practical, resourceful solution to the challenge of lifting heavy materials ever higher without needing external scaffolding structures nearly as tall as the tower itself. It's worth slowing further on this crane system, since it represents one of the more clever, if quietly overlooked, engineering solutions embedded within the tower's construction, rather than build separate external scaffolding towers to support conventional cranes. An approach that would have required nearly as much material and effort as the tower itself. Eiffel's engineers designed small, specialized steam-powered cranes capable of climbing the tower's own structure using rails temporarily mounted along its rising legs. As a section of the tower reached completion, workers would dismantle the crane, transport its components upward using the very lifting mechanism it was about to replace, and reassemble it at the next working level, ready to continue hoisting materials for the section above. This self-climbing crane system needed to be repeated numerous times throughout the tower's construction, each relocation requiring careful coordination to avoid any interruption in the steady, continuous flow of iron pieces arriving from the workshop at Levallois-Perret. A brief pause in crane availability could quickly create a bottleneck, with prefabricated pieces accumulating at the base faster than they could be lifted into position, a genuine logistical concern given the tight 2-year deadline, and one that required careful scheduling between the workshop's production rate, the wagon transport arriving daily from Levallois-Perret, and the construction site's own lifting capacity at any given stage of the project. Visitors to Paris throughout 1888 could watch from the streets below as the tower's distinctive silhouette gradually took shape. A spectacle that, whatever public controversy still surrounded it, undeniably captured the city's attention and curiosity day by day as the ironwork rose steadily higher above every other structure in Paris. Let's slow down once more and imagine an ordinary Parisian family gathering at a small cafe near the Champ de Mars on a quiet Sunday afternoon in the summer of 1888. A mother and father sit with their 2 children, watching, along with dozens of other curious onlookers, as workers move carefully across the tower's rapidly rising ironwork, hundreds of feet above the ground. The younger child, perhaps 6 or 7 years old, points upward in amazement, asking her father how the tiny figures moving along the distant iron beams managed to stay balanced at such an impossible height. Her father, like most ordinary Parisians, following the project's progress through newspaper reports and simple observation, doesn't fully understand the wind resistance mathematics or the precise prefabrication system we've discussed at length tonight. He simply tells her, honestly, that very clever engineers have figured out exactly how to build it safely, piece by careful piece, and that soon, if she's patient, she'll be able to climb all the way to the top herself and see the whole city spread out below her. This kind of ordinary, curious observation repeated itself constantly throughout 1887 and 1888 among Parisians who held no strong opinion in the newspaper debates between artists and engineers, but who found themselves nonetheless quietly fascinated by the strange, ambitious structure rising steadily above their familiar rooftops. For every passionate letter published in Le Temps, there were likely hundreds of ordinary families like this one, gathering casually to watch, developing over many months as a kind of gradual, affectionate familiarity with the tower long before its official completion. Perhaps the earliest, quietest seeds of the public affection that would eventually overwhelm the initial controversy entirely. Once the Tower A opened its platforms to ordinary visitors like this family the following year, Han Holgeramava. By early 1889, the tower's upper sections neared completion, the ironwork narrowing dramatically as it approached its final height. The uppermost sections required particularly careful handling, given both the extreme height involved and the smaller, more delicate scale of the components used near the tower's apex, compared to the massive foundational ironwork far below. On March 31st, 1889, Gustave Eiffel himself climbed the tower's stairs, the elevators not yet being fully operational for the ceremonial occasion, to personally plant a French flag at the tower's summit, marking the structure's official completion. Eiffel was accompanied on this ceremonial ascent by a small group of government officials and members of the press, along with a few of the engineers most closely involved in the project's realization. The climb entirely by stairs took a considerable amount of time and effort, a small preview of the endurance later required of ordinary visitors climbing the tower before its elevators became fully reliable. At the summit, standing at what was now unambiguously the tallest human-made structure on Earth, surpassing the Washington Monument, which had held that title for only a few years prior, Eiffel gave a brief speech and the French flag was raised, accompanied by a 21-gun salute fired from the tower's base. The tower's official height, at completion, measured 312 meters, later extended somewhat further with the addition of broadcasting antennas in the 20th century, a height that would remain unmatched by any structure on Earth for the next 41 years, until the completion of the Chrysler Building in New York City in 1930. Remarkably, the entire project, from the first foundation excavation to this ceremonial flag raising, had taken only 2 years, 2 months, and 5 days, an extraordinarily fast timeline for a structure of this unprecedented scale, made possible almost entirely by the careful prefabrication system, precise surveying, and disciplined riveting process we've walked through slowly tonight. Let's slow down for a while and consider a problem that, on the surface, sounds almost trivial, but very nearly threatened the tower's entire practical purpose. How do you build an elevator that travels up a curved path? Most elevators, then as now, move in a simple, straight vertical shaft. But the Eiffel Tower's 4 legs, for the lowest and most dramatic section of their climb, aren't vertical at all. They lean inward, curving gradually before straightening out higher up the structure. A conventional elevator simply couldn't function along a path like that. This was, in fact, one of the more urgent unsolved problems as construction progressed through 1888. Since the fair's organizers were counting heavily on visitors being able to ascend comfortably, rather than facing an exhausting climb of hundreds of stairs, which would have severely limited how many people could actually experience the tower's upper platforms during the fair's limited 6-month run. Eiffel's own engineering firm designed hydraulic elevator systems for 2 of the tower's 4 legs, using a clever articulated mechanism, essentially a chain of linked pistons capable of following the curved path of the tower's lower structure smoothly, adjusting their angle gradually as the cabin rose. For the remaining 2 legs, Eiffel turned to outside expertise, contracting with an American company, Otis Elevator, already well regarded internationally for elevator engineering, to design a separate, similarly capable system. This decision to bring in Otis wasn't without its own quiet controversy at the time, given the strong nationalistic pride surrounding the project. Some critics grumbled at the idea of an American company contributing meaningfully to what was meant to be a proud showcase of French engineering achievement. But practicality, as it so often did throughout this project, won out over pure national sentiment. The elevators needed to work reliably, safely, and impressively for the millions of visitors expected during the fair, and Otis's expertise offered the surest path to achieving that. Both systems ultimately succeeded, allowing visitors to ascend from the base all the way to the 2nd platform in a matter of minutes. Rather than facing the lengthy, exhausting stair climb Eiffel himself endured during his ceremonial ascent to plant the flag, a separate additional elevator system was later installed to carry visitors the remaining distance to Tower's very summit, completing the full ascent experience visitors enjoy today. There's a quiet lesson, perhaps, in this small chapter of the story. For all the mathematical elegance of Eiffel's wind-resistant curve, and all the disciplined precision of the prefabrication system, the tower's actual public success depended just as much on a much more ordinary, practical problem: simply getting people safely and comfortably up and down, without exhausting them before they'd even reached the view they'd come to see. Grand engineering, it turns out, is rarely only about the dramatic, headline-worthy calculations. Often, it's equally about solving the smaller, more mundane problems standing quietly in the way of the larger vision. The 1889 Exposition Universelle officially opened on May 6, 1889, with the Eiffel Tower serving exactly the dramatic, symbolic role its original design competition had envisioned: an enormous archway entrance, towering above the fairgrounds, immediately recognizable and unlike anything visitors had ever encountered before. Visitors could ascend the tower using hydraulic elevators, engineered specifically to handle the tower's unusual curved legs, a genuine technical challenge in itself, since conventional straight-shaft elevators couldn't easily accommodate the tower's inward-leaning lower structure. The view from the tower's upper platforms offered something entirely new to nearly everyone who experienced it. A genuine bird's-eye perspective of an entire city, from a height no ordinary person had ever previously been able to reach. Nearly 2 million visitors climbed the tower during the 6 months of the World's Fair alone, making it, almost immediately, one of the most visited attractions in the world. Public sentiment, which had been so sharply divided during construction, began shifting noticeably once visitors actually experienced the tower firsthand. The controversial iron latticework that critics had once described as monstrous now struck many visitors as genuinely elegant, almost delicate. When viewed up close, its open, airy structure allowing light to pass through ways a solid stone monument never could. Even some of the tower's earlier critics reportedly softened their opposition once they experienced the structure directly, rather than simply reacting to its presence from a distance. The tower had been granted only a 20-year permit, after which the city intended to dismantle it, recovering the valuable iron for other uses, much as ancient builders once repurposed pyramid casing stones for entirely new structures. For nearly 2 decades, the tower's future genuinely remained uncertain, its eventual demolition seemingly all but assured once its original permit expired in 1909. What ultimately saved it wasn't nostalgia or aesthetic appreciation, but something far more practical. The tower's height, so contested and controversial during its construction, turned out to be extraordinarily useful for an entirely new technology just beginning to emerge: wireless radio transmissions. Beyond the tower itself, the 1889 Exposition Universelle spread across an enormous area of central Paris, showcasing pavilions from dozens of participating nations, along with grand exhibition halls devoted to machinery, fine arts, and the products of France's colonial territories. Visitors could wander through the Galerie des Machines, an enormous iron and glass exhibition hall showcasing the latest achievements in industrial machinery, itself an impressive engineering feat, though one now largely forgotten, compared to the tower that has endured so much more prominently in public memory. Thomas Edison attended the fair in person, exhibiting his phonograph to enthusiastic Parisian audiences, and reportedly climbed the Eiffel Tower himself, later describing his admiration for Eiffel's engineering in warm terms during a private meeting between the two men held, fittingly, within Eiffel's own apartment near the tower's summit. Buffalo Bill Cody brought his famous Wild West show to Paris that same year, performing nearby to enthusiastic French crowds curious about the American frontier. A small reminder that this era's great fairs were as much about cultural exchange and spectacle as they were about pure industrial achievement. Amid all of this, the machinery halls, the international pavilions, the traveling performances, it was the tower that visitors remembered most vividly, and the tower whose image endured longest in photographs, postcards, and popular memory, long after the rest of the fairgrounds were dismantled and largely forgotten. By the time the fair closed in October of 1889, the tower had firmly established itself as far more than a temporary entrance archway. It had become, in the span of just a few months, the genuine centerpiece of the entire event. Exactly the outcome the original 1884 design competition had hoped for, though few, at the time, could have predicted just how completely the tower would come to overshadow everything else built for the occasion. In the years following the tower's completion, radio technology developed rapidly, and Gustav Eiffel, ever the practical engineer, recognized an opportunity to demonstrate the tower's ongoing usefulness beyond its original purpose as a temporary fairground centerpiece. Eiffel funded early radio transmission experiments himself, using the tower's considerable height to achieve broadcastings that shorter antennas simply couldn't match. By 1903, military radio operators were using the tower for long-distance communication experiments. By 1910, France's military had recognized the tower's strategic communication value seriously enough to justify extending its original demolition permit significantly. The tower's role expanded further during the First World War, when its radio transmission capabilities were used to intercept German military communications, including, according to some historical accounts, communications that contributed to the identification and capture of the notorious spy Mata Hari. By providing this genuine, practical, ongoing military and civilian value, the tower transformed, in the public and governmental imagination, from a temporary, controversial fairground novelty into permanent, essential infrastructure. The planned demolition was quietly and then permanently abandoned. It's worth slowing down further on just how significant this radio chapter truly became, since it represents perhaps the single most important turning point in the tower's entire history, more consequential, in practical terms, than even its dramatic construction or its ceremonial opening. In the years immediately following 1909, when the tower's demolition permit was extended specifically due to its radio value, French military and civilian authorities began investing considerably in expanding the tower's communication capabilities. By the outbreak of the First World War in 1914, the tower's radio transmitter had become one of the most powerful in the world, capable of communicating with military forces across considerable distances and playing a genuinely important role in French military communications throughout the conflict. The tower's radio station also broadcast time signals used by ships at sea for accurate navigation, and later, as civilian radio broadcasting emerged in the 1920s, the tower began transmitting some of France's earliest public radio programming, reaching listeners across the country from its unmatched vantage point above Paris. By the 1930s, the tower had added television broadcasting capabilities as well, once again finding renewed practical purpose as new communication technologies emerged, each one benefiting from precisely the height that had once seemed to its harshest critics entirely unnecessary and purely self-indulgent. There is something almost poetic in this pattern, repeating itself across decades. Each time, a new communication technology emerged: radio, then television, then eventually the mobile phone and broadcast antennas, still mounted near its summit today. The tower's height, so bitterly contested in 1887, proved itself useful all over again, in ways its original critics and even its original defense could scarcely have anticipated. What began as a mathematically elegant solution to a design competition brief had become something else entirely. A piece of genuinely useful, load-bearing national infrastructure secured in permanence not by artistic appreciation but by radio waves. There is something worth sitting with in that turn of events. The very height that provoked such fierce aesthetic objection from Paris's cultural establishment ended up being precisely the quality that saved the tower from the fate its original permit always assumed it would meet. Function, in the end, preserved what controversy alone might never have protected. Let's slow down once more and imagine a quiet evening sometime in the early 1900s, many years after the tower's completion. Gustav Eiffel, now considerably older, sits in a small private apartment he maintained near the very top of the tower itself. A genuine, furnished space he used both for entertaining distinguished guests and for conducting his own ongoing scientific experiments, particularly related to meteorology and aerodynamics. Fields he pursued with considerable seriousness following the tower's completion. From his window, he can see all of Paris spread below him, the same city whose cultural elite once petitioned so passionately against the very structure he now calls, in some sense, a second home. He has spent recent years using the tower for wind resistance experiments, dropping various shaped objects from its heights to study air resistance. Early, practical research that would later contribute meaningfully to the emerging science of aerodynamics, relevant to the aircraft designs, beginning to emerge in this same period. There is a quiet satisfaction, perhaps, in having built something that continues to find new purpose years after its original, temporary role as a World's Fair entrance archway had technically expired. The controversy of 1887 must feel by now like a distant memory. The passionate newspaper letters, the artists' committee, Maupassant's reported lunches inside the one place in Paris where the tower couldn't be seen. Eiffel, ever the engineer rather than the artist, likely never sought to win that particular argument through rhetoric or persuasion alone. He let the structure itself make its case, slowly, patiently over years, rather than newspaper columns. First through the sheer wonder of the view it offered visitors, and later through the genuine practical usefulness it demonstrated once radio technology gave its height renewed purpose. Sitting quietly in his apartment, high above a city that has, by now, largely embraced the tower as a defining symbol of Paris itself, Eiffel may have felt, if only briefly, something like quiet vindication. Not loud, not triumphant, simply the calm, settled satisfaction of a careful engineer, watching his calculations continue to hold, exactly as intended, high above the rooftops of the city that once so passionately doubted him. Eiffel's scientific curiosity, hinted at in the previous section, deserves a slower, more detailed look, since it represents a genuinely important chapter in the tower's ongoing story, separate from the drama of its original construction and public reception. Following the tower's completion, Eiffel gradually shifted much of his professional attention away from new construction projects and towards scientific research, using his own creation as a uniquely valuable research instrument. He established a small meteorological station near the tower's summit, using its unprecedented height to gather atmospheric data, wind speed, temperature variation, and air pressure readings at an elevation simply unavailable to most researchers of the era, who lacked access to any comparably tall structure. Eiffel also conducted a series of practical aerodynamic experiments, dropping variously shaped objects from the tower and carefully timing and measuring their descent, gathering early data on air resistance that would later prove genuinely useful to the emerging field of aviation engineering. At a time when powered flight remained a very new and uncertain pursuit. In 1909, recognizing the limitations of dropping objects from a fixed height, Eiffel constructed a dedicated wind tunnel laboratory at the base of the tower, later relocating this research facility to a nearby location as his aerodynamic studies grew more sophisticated and demanded more controlled experimental conditions than simple object dropping could provide. This wind tunnel, built and operated well into Eiffel's later years, contributed meaningfully to the broader scientific understanding of aerodynamics during the crucial early decades of aviation development, studied by engineers and aircraft designers eager to understand how various shapes and surfaces behaved when moving through air at speed. There's a pleasing symmetry in this chapter of the story, worth sitting with quietly before we move toward tonight's close. The very mathematics that shaped the tower's wind-resistant curve, calculated so carefully by Coquelin and Nouguier back in 1884, eventually inspired Eiffel himself to spend his later years deepening humanity's broader understanding of exactly the forces his tower had been so carefully designed to resist. The tower, in other words, didn't simply stand as a finished monument to one engineering achievement. It continued, for decades afterward, to actively generate new knowledge, new research, and new understanding. A structure that kept working, kept teaching, long after its ceremonial flag raising in March of 1889. It's worth pausing, as we did with the pyramid, to consider the actual materials and tools involved in raising this tower, because, much like ancient Egypt's copper chisels, the toolkit here was simpler than the achievement might suggest. The tower's primary material was puddled iron, sometimes called wrought iron, a material chosen deliberately over steel, which was, at the time, a newer and somewhat less consistently reliable material for a structure of this scale and importance. Puddled iron offered excellent resistance to corrosion when properly maintained, along with predictable, well-understood structural properties that Eiffel's engineering team could calculate with confidence. The tower required approximately 7,300 tons of this iron in total, assembled from those 18,000 individually prefabricated pieces we discussed earlier. Beyond the iron itself, the riveting process required simple but effective tools, portable forges to heat rivets to the necessary temperature, heavy hammers for driving them into place, and the dolly tool used to brace the opposite end during hammering. Scaffolding and temporary wooden platforms supported workers at various stages of construction, gradually repositioned upward as work progressed, much like the ramps that once rose alongside the growing pyramid in our previous episode. Steam-powered cranes, mounted directly onto the tower's own structure, provided crucial lifting capability at height, themselves periodically dismantled and reassembled at progressively higher positions as the tower grew, since no external structure of comparable height existed to support conventional crane placement. Paint, too, played a genuinely important structural role, not merely a cosmetic one. Eiffel's team applied several coats of paint to protect the iron from corrosion, a maintenance practice that continues to this day. The tower is repainted approximately every 7 years, requiring around 60 tons of paint applied entirely by hand by specialized painters trained to work safely at extreme height. The tower's paint color has actually changed several times throughout its history, from an initial reddish brown through several different shades over subsequent decades, before settling on the distinctive, slightly darkened bronze tone applied today. A color chosen partly for aesthetic reasons, and partly because it appears to blend attractively against the Parisian sky in most lighting and weather conditions. Much like the pyramid's original gleaming white casing has long since been stripped away, revealing a rougher, more weathered appearance today. The Eiffel Tower's current color represents just one chapter in a longer, evolving visual history. A reminder that even our most iconic monuments are rarely static, unchanging objects, but rather structures that continue to be maintained, adjusted, and cared for year after year, long after their original construction concludes. It's worth slowing down a little further on this repainting process, since it remains, even today, one of the more remarkable ongoing maintenance efforts of any major monument in the world. Each repainting cycle takes approximately 18 months to complete, carried out by a specialized team of painters trained specifically to work safely at extreme height, often suspended from ropes and platforms along the tower's iron lattice, much the way Etienne and his riveting team once worked more than a century earlier. The paint itself must be applied entirely by hand, brush by brush, section by section, since the tower's intricate lattice structure, with its countless individual beams, joints, and connection points, simply isn't suited to the kind of large-scale spray equipment used on flatter, simpler structures. Painters work in careful sequence, one section of the tower at a time, gradually working their way around and up the entire structure, repeating a process that, once finished, will already need to begin again in roughly 7 years, as weather and corrosion slowly wear away at the protective coating. This means the tower has now been repainted more than 20 times throughout its history, an ongoing, cyclical commitment considerably different from the ancient pyramid's original builders, who quarried, transported, and assembled their structure once, then largely left it to endure on its own for millennia, protected mainly by the simple durability of stone rather than continuous, active maintenance. The tower, by contrast, requires this active, ongoing care to survive as elegantly as it does, a living structure, in a sense, dependent on each generation's willingness to continue tending to it, rather than a monument that simply endures passively, untouched, the way the pyramid largely has. Beyond its physical presence in Paris, Eiffel Tower has achieved something few structures in human history ever manage. It has become one of the most reproduced, replicated, and instantly recognizable silhouettes on the entire planet. Smaller replicas of the tower exist in cities around the world. A half-scale version stands in Las Vegas, Nevada, incorporated into a hotel and casino complex. Another exists in Shenzhen, China, part of a themed park recreating famous world landmarks. Smaller souvenir versions, ranging from tabletop models to keychain trinkets, are produced by the millions annually, sold to tourists in Paris and shipped to gift shops across the globe. The tower's distinctive silhouette appears constantly in film, photography, and popular culture, often used as an immediate visual shorthand for the city of Paris itself, or for romance, elegance, and European charm more broadly. A symbolic weight the tower's original artistic critics could scarcely have imagined it would eventually carry, given how fiercely they once argued it would permanently disfigure the city's visual identity. Today, the tower is illuminated each evening by thousands of small lights, installed initially for the Millennium celebrations at the turn of the 21st century, and maintained ever since, creating a distinctive twinkling sparkle effect that runs for several minutes at the start of each hour after sunset. A modern addition Gustav Eiffel himself never witnessed, yet one that feels, in its own way, consistent with his original spirit of confident, forward-looking engineering applied to public spectacle and delight. There's something worth appreciating quietly in this transformation from controversial industrial intrusion to beloved global symbol, replicated and celebrated in cities the tower's original builders never visited, by people who, more than a century later, still climb its stairs and platforms in wonder, much as those first 2 million visitors did during the summer and autumn of 1889. The Eiffel Tower has now stood for well over a century, considerably less time than the Great Pyramid we explored in our previous episode, but a genuinely long span nonetheless, filled with remarkable events witnessed from its unique vantage point above the city. It witnessed the final years of the Belle Epoque, the vibrant cultural period in Paris during which it was originally built, a time of rapid technological change, artistic innovation, and confident optimism about the future. It witnessed the outbreak and devastation of the First World War, during which its radio capabilities served the practical military purpose that ultimately secured its survival. It witnessed the German occupation of Paris during the Second World War, during which, according to popular historical accounts, French resistance workers deliberately cut the tower's elevator cable, forcing German officials, including Adolf Hitler during his brief visit to occupied Paris, to either climb the stairs themselves or forego the summit entirely. Hitler, notably, chose not to climb, viewing the city instead from ground level. It witnessed the liberation of Paris in 1944 and the jubilant crowds that gathered at its base to celebrate the city's freedom. It witnessed the tower's own gradual transformation from a controversial, temporary fairground novelty into perhaps the single most recognized silhouette of any building on Earth, reproduced endlessly in photographs, films, postcards, and countless smaller replicas found in cities around the world. Today, the tower welcomes approximately 7 million visitors annually, making it consistently one of the most visited paid monuments anywhere on the planet. A remarkable outcome for a structure that, at various points in its early history, seemed destined either for fierce cultural rejection or for eventual planned demolition. It witnessed, too, quieter, more personal moments scattered across its long history. Countless marriage proposals made on its platforms, families gathering for photographs across generations, and travelers from every corner of the world pausing, often in genuine, quiet awe at their first close view of a structure they may have photographed 1,000 times before, yet never quite grasped the true scale of, until standing directly beneath it. It witnessed the arrival of television broadcasting antennas in the mid-20th century, extending its practical usefulness yet again, much as radio once had decades earlier, ensuring the tower remained relevant infrastructure well into an era of technology its original 1889 visitors could scarcely have imagined. It witnessed, in 2003, a fire that broke out near its summit, contained relatively quickly by emergency crews, causing only modest damage and briefly closing the tower to visitors. A rare moment of genuine vulnerability for a structure so often taken for granted as permanent and indestructible. It witnessed the tower's own centennial celebration in 1989, exactly 100 years after Gustave Eiffel first raised the French flag at its summit, marked by fireworks, public celebration, and a general sense of affectionate pride from a city that had by then thoroughly embraced the tower as an inseparable part of its own identity, a striking contrast to the passionate rejection expressed by so many prominent cultural figures exactly a century earlier. Unlike the pyramid, built for eternity by builders who genuinely believed in an eternal afterlife, the Eiffel Tower was built, quite explicitly, as something temporary, a 20-year experiment, never intended to become the permanent symbol it eventually was embraced as. There is something worth appreciating quietly in that difference. Not every enduring structure was built with permanence in mind from the very beginning. Sometimes, a temporary solution to an immediate practical problem. In this case, a striking entrance archway for a 6-month World's Fair finds, through circumstance, usefulness, and simple persistence, a permanence its original builders never fully anticipated. Even today, the Eiffel Tower holds a handful of small, pleasant curiosities worth sitting with. Before we close tonight's story, the tower actually grows slightly taller during the summer months due to thermal expansion of its iron structure in warmer temperatures, typically rising somewhere between 15 and 20 centimeters compared to its height during colder winter months, before contracting back down as temperatures cool again each year. This thermal expansion also causes the tower to lean very slightly away from the sun during the hottest parts of the day, as the iron on the sun-facing side warms and expands marginally more than the shaded side, a subtle, almost imperceptible tilt of just a few centimeters, invisible to the naked eye but measurable with precise instruments. The tower briefly held the title of the world's tallest structure for slightly longer than we mentioned earlier, would initially suggest, with some historical sources noting that a radio antenna added in 1957 extended its total height further still, keeping it relevant in height-based records, even as purely architectural structures elsewhere eventually surpassed its original unadorned measurement. Gustave Eiffel's name, along with the names of 72 other notable French scientists, engineers, and mathematicians, is inscribed around the tower's first-level frieze, a quiet, easily overlooked tribute to the broader scientific and engineering tradition Eiffel's own achievement both drew from and extended. And perhaps most charmingly, the tower's private apartment, the same one we imagined Eiffel occupying earlier tonight, remains preserved today, furnished in period style, viewable by visitors who make it to the tower's uppermost level, a small, quiet window into the personal, human side of a project, so often remembered only for its scale and controversy. There is something gently reassuring in these small, ongoing details. The seasonal expansion and contraction, the periodic repainting, the careful preservation of Eiffel's own quarters. The tower isn't a static, frozen monument, sealed away from time the way the pyramid's inner chambers were beneath solid stone. It continues, quiet to breathe with the seasons, to be maintained by careful hands, to remain, in small ways, alive and responsive to the world around it, even as it approaches its 140th year of quietly watching over the city that once so passionately doubted it. Let's slow down once more and imagine a different kind of evening. Not at the construction site this time, but in a quiet Parisian salon, sometime in early 1887, not long after the artist's protest letter appeared in Le Temps. A small gathering of writers and painters has assembled, as they often did in this era, to discuss the news of the day over wine and conversation. The tower, still only partially built, its four legs just beginning to rise above the rooftops nearby, dominates much of the discussion. One guest, an architect, describes the structure in exactly the terms used in the published letter. Monstrous, useless, an industrial intrusion into a city defined for centuries by stone and elegance, rather than exposed iron and rivets. Another guest, a younger painter, offers a quieter, more hesitant dissent. He admits, somewhat reluctantly, that he finds something strangely compelling in the tower's skeletal framework, particularly at dusk, when its ironwork catches the last orange light of the setting sun against a darkening sky. The architect scoffs gently at this observation, insisting that mere visual curiosity is no substitute for genuine architectural merit, and that Paris deserves monuments worthy of its historic grandeur, not a temporary industrial curiosity built for a passing fair. This same conversation, in one form or another, was likely repeated countless times across Paris throughout 1887 and 1888. Genuine, sincere disagreement among educated, thoughtful people about what a great city's skyline should represent and whether raw engineering achievement alone could ever qualify as true beauty. It's worth remembering tonight that this debate wasn't simply small-minded resistance to progress as it's sometimes retold today. The signatories of that famous protest letter was serious, accomplished cultural figures, genuinely concerned about preserving something they valued deeply. Faced with a rapid, irreversible change to the city they loved, they were not entirely wrong to feel uncertain. Cities do change permanently when structures of this scale and prominence rise within them, and reasonable people can genuinely disagree about whether such change represents progress or loss. What makes this particular story so interesting, in hindsight, isn't that the critics were foolish and Eiffel was simply, obviously, right all along. It's that time itself, patiently, quietly, eventually settled the argument in a way neither side could have fully anticipated in 1887, not through further debate or persuasion, but through simple, accumulated, everyday familiarity, and later, through the tower's unexpected practical usefulness once radio technology arrived. The young painter in our imagined salon, watching the tower catch that orange evening light, may have sensed something the architect couldn't yet see. That beauty, sometimes, needs time and repeated exposure to fully reveal itself, particularly when it arrives in an unfamiliar new form. Behind every dramatic engineering achievement lies a far less glamorous, but equally essential story. How, exactly, does one pay for it? The French government, while enthusiastic about the tower's potential as a symbol of national engineering prowess, was unwilling to fund the entire project through public money alone. Eiffel's contract with the government covered only a portion of the estimated construction costs, with the understanding that Eiffel himself would need to secure the remaining funding privately in exchange for receiving all revenue generated by the tower during its first 20 years of operation. including ticket sales for visitors ascending to its platforms. This arrangement placed genuine financial risk directly onto Eiffel's own shoulders. If the tower failed to attract sufficient public interest once completed, he stood to lose considerably more than simply his professional reputation. Eiffel responded to this challenge by establishing a dedicated company, funded partly through his own considerable personal wealth accumulated across his earlier engineering career, and partly through a syndicate of French banks willing to invest in the project, persuaded by Eiffel's strong prior reputation and the detailed, confident engineering calculations underpinning his proposal. This financial structure created an additional layer of pressure atop the already demanding 2-year construction deadline. Every month of delay meant not just a tighter timeline before the fair's opening, but real, accumulating financial exposure for Eiffel and his investors, who were counting on ticket revenue from millions of expected visitors to eventually recoup their investment. As it turned out, this financial gamble paid off remarkably well. The nearly 2 million visitors who climbed the tower during the World's Fair alone generated enough revenue to recoup nearly the entire construction cost within nowhere near the full 20-year revenue window Eiffel had originally been granted, a testament to just how enormously popular the tower became. Almost immediately upon opening, despite the passionate cultural criticism that had surrounded its construction only months earlier, there's a practical lesson quietly embedded in this financial side of the story, one easy to overlook amid the more dramatic tales of ironwork and wind calculations. Even the most mathematically elegant, structurally sound engineering achievement still depends, in the end, on ordinary practical questions. Who pays for it? Who bears the risk if it fails? And whether enough people will actually be willing to visit once it's finally built. Eiffel understood this as clearly as he understood wind resistance and iron tensile strength, and his willingness to personally shoulder financial risk, alongside his engineering confidence, proved just as essential to the tower's ultimate success as any single calculation in his famous curved design. It's worth remembering tonight that the Eiffel Tower's design wasn't the only ambitious tower proposal circulating in this era of rapid industrial confidence. Several years before the Paris design competition, British engineers had proposed a similarly enormous iron tower for London, intended to rival or exceed anything built in France. A project that progressed only as far as a partially completed base before financial difficulties brought construction to a permanent halt, leaving behind an unfinished structure eventually demolished entirely. Its ambitions never fully realized. American engineers, too, floated various proposals throughout the late 19th century for towers exceeding even the Eiffel Tower's eventual height, part of a broader spirit of competitive, confident engineering ambition characteristic of this particular industrial era, when iron and steel's construction techniques were advancing enough that height records seemed almost destined to be broken again and again, year after year. Few of these rival proposals ever moved beyond preliminary sketches and enthusiastic newspaper coverage. What set Eiffel's tower apart, ultimately, wasn't merely ambition, but the same disciplined, patient engineering approach we've traced throughout tonight's story. Careful wind resistance mathematics, methodical prefabrication, precise surveying, and a genuinely realistic, achievable construction timeline. backed by an engineer with a proven record of delivering exactly what his calculations promised. Ambition alone, it turns out, rarely completes a tower. Ambition, paired with patient, disciplined method, is what actually raises one successfully above the rooftops and keeps it standing more than a century afterward. If you joined us for our very first episode, The Story of the Great Pyramid, you might notice something interesting in comparing these two structures separated by well over 4,000 years, yet connected by the same basic human impulse to build something taller, more ambitious, more enduring than anything attempted before. The pyramid was built slowly, deliberately, over 20 years, using methods refined across generations of prior experimentation by a workforce numbering in the tens of thousands, motivated by deep religious conviction about eternity and the afterlife. The Eiffel Tower was built quickly, urgently, in just over 2 years, using methods invented specifically for this project by a workforce numbering in the hundreds, motivated by a temporary contract, a 6-month World's Fair deadline, and Gustave Eiffel's own confident belief in mathematical elegance. The pyramid was built to last forever, its builders genuinely intending permanence from the very first surveyed line in the desert sand. The tower was built to last 20 years, its very permit assuming its own eventual demolition, its survival ultimately secured not by original intention, but by an entirely unforeseen new technology. And yet, despite these profound differences in philosophy, timeline, and purpose, both structures share something remarkable in common. Both required extraordinarily careful mathematics, calculated using tools and methods considered basic or old-fashioned by the very next generation of engineers, and yet accurate enough that both structures continue standing, structurally sound, long after their original builders' lifetimes. Both required a disciplined, repeatable system for translating enormous, ambitious designs into manageable, individual components, whether that meant 2 million individually quarried limestone blocks or 18,000 individually prefabricated iron pieces, each one carefully labeled, tracked, and installed in its correct sequence. Both required a workforce willing to perform repetitive, physically demanding labor at genuine personal risk, motivated by some combination of practical necessity, cultural pride, and in at least one case, deep spiritual belief. And both ultimately outlasted the controversy, doubt, or uncertain purpose that once surrounded their construction. The pyramid quietly enduring through millennia of shifting empires and religions, the tower enduring through newspaper protests, a temporary permit, and near-certain planned demolition. There's a gentle, reassuring thought worth carrying with you into sleep tonight, drawn from both of these stories. Ambitious things, built carefully and patiently enough, have a tendency to outlast the doubts that once surrounded their beginning. Whether built for eternity, like the pyramid, or built merely to survive 20 controversial years, like the tower, both structures remind us that patient, careful work, rivet by rivet, stone by stone, has a way of quietly proving its own worth over time, long after the arguments and uncertainties of its construction have faded into history. And so, slowly, very slowly, our tower is complete. Every rivet driven, every calculation checked and checked again, every iron leg nudging precisely, exactly where the mathematics said it would. Every measure of doubt eventually met with quiet, patient usefulness. If you're still awake, that's all right. There's no need to follow the story any further tonight. There's nothing left to build, nothing left to rivet or hoist or calculate. Just let it rest now, the way the tower itself has learned to rest, swaying only slightly in even the strongest Parisian winds, exactly as Gustave Eiffel's careful curve always intended it to. Somewhere right now, far across an ocean, or perhaps just a short distance from wherever you are lying comfortably tonight, the Eiffel Tower is standing quietly in the dark, its iron lattice catching faint moonlight, the way it has for over 130 years, the sign moving slowly beneath it, the same patient river that once floated caissons and construction barges toward its riverside foundation. Somewhere near its summit, a small private apartment sits preserved and empty, exactly as Gustave Eiffel once furnished it, waiting quietly for tomorrow's visitors. Somewhere below, in a quiet Parisian suburb, the old workshop grounds at Levallois-Perret carry on with entirely different work now. The drafting tables and rivet hole calculations of Pierre and his colleagues long since faded into the ordinary passage of time, remembered now only in old company records and the patient stonework of history. Nothing to build tonight, nothing to rivet, nothing to measure, just stillness, just iron, just time moving slowly, patiently, the way it always has, over rooftops, over rivers, over quiet monuments that have long since stopped counting the years. Let your breathing slow, the way the tower sways gently and returns, always, to its resting position. Let your body settle, the way iron settles into its calculated curve. Let your thoughts drift quietly away, the way faint moonlight drifts across an open iron lattice, with nowhere urgent left to be. Somewhere, high above a sleeping city, a lattice of iron holds perfectly still against a dark sky, exactly as it was calculated to, exactly as it has for over a century, asking nothing of the world except to be left standing quietly until morning. You can rest the same way. Quietly, steadily, with nothing left to hold up tonight except your own tired, comfortable body settling gently into sleep. Rest now. This has been Sleepy Construction. Good night.